Hello. Today we're going to continue on into Unit 2, and this section is called Postulates, using Postulates and Theorems. So we are going to define several postulates and just utilize them within problems. Excuse me. So first of all, a postulate is really just, it's kind of like a definition. It's really a basic rule. The formal definition is they are just rules we use without having to prove them. So I feel like they are more basics of geometry. Theorems, on the other hand, require multiple postulates to create, and we will go through proving lots of theorems, but we will also just use theorems throughout our work. All right, so we've got, if you take a look here, we have postulate 5, 6, 7, 8, 9, 10, 11. Now those numbers simply align to our textbook. We do have a textbook that we follow along, although most of your homework is in Schoology. So most textbooks just number things in order that they appear. So these names really have no meaning. In fact, I don't want you to ever use these names. I'll just cross them out because the name is meaningless. It doesn't have anything to do with the postulate. It just happened to be the order it came in. So what we're going to do is actually write out the postulate when we use it. Okay, so these are going to sound familiar to you. We've already studied these with points, lines, and planes. Through any 3 points, there exists exactly one line. Through any 2 points. Through any 2 points, there exists exactly one line. Okay, we actually wrote that down really within our first section on points, lines, and planes. A line contains at least 2 points. So I feel like the second postulate is like the opposite of the first. So the first postulate says, if you have the points to start with, there exists a line. If you have the line to start with, it contains at least 2 points. Okay. If 2 lines intersect, then their intersection is exactly 1 point. Okay, so 2 lines are going to always intersect at 1 point. The next one. Through any 3 non-collinear points, there exists exactly 1 plane. So non-collinear. Okay. Through any 3 non-collinear points, there exists exactly 1 plane. And then the next one's kind of the reverse of this one. A plane contains at least 3 non-collinear points. Non-collinear. So again, the first one, you start with the points. If you have 3 non-collinear points, then there is 1 plane. If you have the plane to begin with, then it contains at least 3 non-collinear points. Okay, next couple. If 2 points lie in a plane, then the line containing them lies in the plane. So let's write this down and talk about it. Lies in the plane. So this kind of ties in, if you have 2 points, then you're going to have a line, okay? So if you've got 2 points in a plane, then the line that goes through them is also in the plane. So some of these postulates are pretty basic. So you might think to yourself, well, of course it lies in the plane. That seems obvious, but postulates are kind of the building blocks. If 2 planes intersect, then their intersection is a line. Okay, so we're going to take these postulates and use them in the 4 examples below. So let me go through the directions, and I might start you out on the first one and maybe have you pause it and try the next few. All right, state the postulate illustrated by the diagram, and then I just put here, write out the postulate, don't use the number, because the numbers really don't mean anything. So these are in the form of, if you're provided something, then the result is this. Okay, so these are all in those conditional if-then statements. So the way I would read this, I would say, if you have a line, then you've got 2 points on the line. Okay, so the line is in the hypothesis. The conclusion would be the 2 points being on the line. So that's going to go with the second one. a line contains at least 2 points. So we have the line to begin with, and then the result is it having at least 2 points. So I'm going to write that down. A line contains at least 2 points. A line contains at least 2 points. Okay. All right, so I want you to pause here. I want you to go through B, C, and D and jot down the theorem, not the theorem, the postulate that it goes with above. Okay, let's go through the last three. So the second one, if you have 3 points, then you have a plane. So it goes with through any 3 non-collinear points, there exists exactly one plane. Letter C, you've got the 2 points, then you've got the line. So C is like the opposite of the first one. So through any 2 points, there exists exactly one line. And then finally, if you have a plane, then you have the 3 points. So a plane contains at least 3 non-collinear points. Okay, so these are going to eventually for you just become, I don't want to use the word definitions, but just become things that you're going to use as you are solving problems. Okay, let's go on to the next page. And we have a few examples here to take a look at. Okay, use the given information to sketch a diagram. So sketch a diagram showing line AB intersecting line CD at point E so that line AB is perpendicular to CD. So if you need to write down perpendicular again, maybe write the word perpendicular above it. So perpendicular means you've got a 90-degree angle. So I'm going to draw 2 lines intersecting at a 90-degree angle, and I'm just going to make sure I name the line AB, CD, and point E. Okay, so it could be something like this. I could have maybe AB more vertical. So I'll have A and B. Doesn't matter, you could have done, you know, AB horizontal. I'm going to have CD going through here at a right angle. So that looks approximately, it's about like a right angle. So I need C and D on this line. I need their intersection point is E. Let's stick an E right there. And then to show it's a right angle, or to show that it's perpendicular, add the right angle in one of the 4 corners. You don't need it in multiple spots, just one. Okay, number 3 says to redraw this example if the given information also states that segment AE is congruent to segment EB. Okay, so that means even though AB is a line here, which is fine, I also could say, well, this is segment AB. So I want to show that segment AE is congruent to segment EB. So I'm going to make it a little bit longer so I have a little bit more space. So I still need A and B. And then CD is coming through here at a right angle. So CD. I need my intersection of E, and I need the right angle, okay? And then I want to put those tick marks to show that AE is congruent to EB. Maybe switch colors here. So I'm just going to put a tick mark on each of those. So that gives me the visual of congruence. Okay, so this, again, pictures are worth everything in geometry. I could tell you a lot about this diagram without having any words in the directions. Okay, there's lots of things going on. So we want to make sure we're getting in the habit of labeling things with tick marks, the right angles, and as we learn new items, we'll add to that. Okay, let's look at maybe number 4 together, and then I'll have you guys wrap up with 5 through 10. All right, interpret a diagram in 3 dimensions. Okay, which of the following cannot be assumed from the diagram? So all points are coplanar. So I see points F, I have an A, a C, E is a point, G, B, D is a point. So are they all on a plane together? Yeah, I mean, honestly, my paper is a plane, okay? These points are on my paper. It's listed here on the diagram. So that's true. I'm just going to jot down a true here. So actually, this is looks like a multiple choice, so that's not going to be the false one. line FG is perpendicular to line CD. So there's FG and there's CD. I mean, they could be perpendicular, but I really need this right angle here, so we can't assume anything. So this, to me, I believe is false, but let's rule this one out. This should be true if B is the right answer. Points C, D, and E are collinear. C, E, and D. C, E, and D. Yes, they are all on this line right here. That's true. So B is going to be our false, or not false, but we can't necessarily assume it. It could be true, but I need that proof. So, you know, tick marks, right angles, things like that are going to be the proof, regardless of how that diagram is drawn. Okay, I want you to pause. I'd like you to read through 5 through 10, and you're going to continue to use this diagram to decide true or false. Okay, number 5. CEF, FED are a linear pair. Yes, they're along a line, they're adjacent, they share the common side. That's true. Angle CEF, so angle CEF right here, is also congruent to angle FED. So those two angles. So are they equal to each other? Well, not necessarily. One could be, I mean, they look like they could be close to 90 each, but one could be like 91 versus 89. So this, we're going to say false. If we can't determine it to be true, it's going to be false. The length of CD is equal to the length of BD. So C over to D, B over to D. Well, I don't know. I don't have any tick marks to show me that. So I'm going to say false right now. Line FG and line CD intersect at point E. FG, CD, yes, I can clearly see the intersection. True. CEF, so CEF right here, and I always go back to the vertex really with my pen or pencil. GED are vertical angles. Where's G at? GED. So I'm going to use my pencil so I can erase this. So we're looking at this angle right here and this angle right here. CEF, GED. Yes, those are vertical angles. Two intersecting lines and the angles across from each other. Okay. And then finally, line FG and line BD do not intersect. FG is right here, and BD do not intersect. Okay, this is tricky because they appear to not intersect on paper. But how do I know that they don't intersect? I mean, one could be like slightly angled one way, and the other could be slightly angled that way, and then they could eventually intersect further on down the plane. So unless I know they're parallel, then I can't assume that they will never intersect. So this is false. So one thing I want to add symbol-wise, if two lines are parallel, and we'll learn this as we encounter parallel lines, they a lot of times either have like a little extra arrowhead somewhere on them, or sometimes it looks like a little colored in triangle. Okay, so we will start, when we start really studying parallel lines, we'll start to talk more about that. But unless the directions tell you something or you see some symbols on there, you can't necessarily assume it's true on some of these items. Okay, well, that's it for this section. If you have any questions, as always, just let me know.